Before starting to solve some exercises from sequences, we review some important points in brief. If I have a sequence an, let's say defined by root n, we call this one general term. We can show by one of these two graphs to the left or to the right on a number line or in two dimension. We can also write the terms of the sequence. If you look at the second diagram here, it shows that the terms of the sequence, if we go forward from 1, 2, 3, 4, and so forth, the terms of sequence are increasing. And in this case, it is called strictly increasing, or it is monotone. Since the terms of sequence goes to infinity, then this sequence is called divergent, or we say an diverges to plus infinity. But all the terms of the sequence are greater than or equal to the first term, and it is called the infimum. So if I want to find infimum of an, it is 1. In the second example, an 1 over n, still the terms of sequence shows that the sequence is monotone. So this is monotone, and that monotonicity, the type of the monotonicity is called strictly increasing. In the second case, still monotone, but this time it is strictly decreasing. The terms of the sequence are all less than 1. It means that the supremum of this sequence is 1. The terms of sequence decreases and the limit is 0, or an approaches 0, then all terms of the sequence are greater than or equal to 0, and infimum of this sequence is 0. This sequence is convergent. All terms are between 0 and 1, so it is bounded. So this sequence is unbounded because from above it goes to positive infinity. There is no upper bound, however, there is a lower bound. We can say that it is bounded from below. Second sequence is bounded from above and also bounded from below. In general, it is bounded. It is convergent, or it converges to 0, and it is monotone, or the type of monotonicity in this case is strictly decreasing. The last one is minus 1 to the n plus 1 times 1 over n. When n approaches infinity, this one also still approaches 0. It means that it is convergent, or it converges to 0. Terms of sequence are between these two values. Means that supremum of this sequence is 1, and infimum of this sequence is this term, which is minus 1 over 2, the second term of the sequence, and the limit is 0. So this one also is bounded, but this last sequence is not monotone. The terms of sequence moving up and down, and this is not monotone. So the first two are monotone, the last one not monotone. The first sequence is unbounded. Second and the third sequence are bounded. If the limit exists, we say the sequence is convergent or converges to this limit. If it goes to infinity or the limit does not exist, we say that the sequence is divergent. In general, sequence is a function whose domain is positive integers or natural numbers. So anything we studied related to functions we can use for the sequences. And related to monotonicity, we know that for a function, if f prime x is positive on an interval, then f is increasing. It means that you can substitute n by x, derivate, and if you get positive, it means that your sequence is increasing. Negative, the sequence is decreasing. But if the derivative is changing the sign, so it is not monotone. This an equal to 2n is called the general term, and these are all terms of the sequence. If we write first term, second term, the nth term, and so forth. A sequence can be written using the explicit form of the general term, or maybe by some starting terms and the general term. If I look at these sequences, an, root 1, root 2, root 3, it shows that it is strictly increasing. It is unbounded, and this is the infimum. Second one, this is not monotone because it changes from positive to negative, so this is not monotone. The limit approaches to 0, it is convergent. And the terms of the sequence are between 1 and minus half, so 1 is supremum, minus half is infimum. So whenever you have minus 1 to the n times something like bn, which is always positive, then this sequence is going to be not monotone. And if you want to find the supremum and infimum, you can write some initial terms, and then it shows that the terms of sequence are going to be most of the time between these two terms. Cn, n approaches infinity, the limit is 1, so this sequence approaches to 1, convergent. The terms of sequence are between 0 and 1. 1 is the infimum, the supremum, and 0 is the infimum. This sequence is divergent, terms of sequence jumping between 1 and minus 1. 1 is supremum, minus 1 infimum. Sequence is bounded. It is not monotone because it is alternatingly changing from 1 to minus 1 and vice versa. And it is not convergent. Definition of the convergence. If we say a sequence is convergent or the limit of the sequence is L, in that case, for any epsilon greater than 0, we need to find some capital N for which, for any n after that, all the terms of sequence lie in an interval like L minus epsilon and L plus epsilon. In some exercises, for a given epsilon, we are going to find the value of n. That guarantees this condition. Or on the diagram, we can show that if the limit exists, it means that for any epsilon greater than 0 here, if I draw this two horizontal lines, this is L, and the limit is L, it means that the terms of sequence are going to be closer and closer to this line. In that case, for any epsilon, we need to find some n for which, for any n greater than n, we know that the difference or the distance between a and an epsilon is less a and an L. This means that the distance between a and an L is less than epsilon. It means that it falls between these two horizontal lines. If the limit of a sequence approaches positive infinity, we say that the sequence diverges to plus infinity, or it is divergent. And we simply write this one. If the sequence diverges to negative infinity, and if the limit does not exist, like minus 1 to the n, in this case the limit does not exist, and we say that the sequence is divergent. So divergency can have different form. The sequence may diverge to plus infinity, minus infinity, or once the limit does not exist, we say that it is divergent. We don't say what type of divergency. Since we define sequence as a function, all the theorems that we studied for functions can be used for sequences as well. For example, for the limit rules, sum rule, difference rule, product rule, constant multiple rule, and quotient rule that we define for limit of functions. Now for sequences a n and bn, if both sequence converges. So if we have two convergent sequences, then we can use this rule. It means that instead of finding the limit of a sequence, which is sum of an and bn, we can study an and bn separately, and then limit of sum is sum of limits, or limit of difference, difference of the limits, and so forth. For the quotient rule, we need to know that b is different from 0, then we can use the quotient rule. This is going to be the most important limit in sequence. When n approaches infinity, this 1 over n has limit 0. And in most cases, like the last one, we are going to keep the dominating term in numerator and denominator. And for example, in this case, the dominating term is the highest power of n if we have only the polynomials. And we can cancel out the infinity factor, and we have minus 7 as the limit. But if you want to use the theorems, we can say that this is a constant multiple of minus 1 and 1 over n. If you rewrite the second one, it can be the difference between 1 and 1 over n. Both has limit. We can find the limits and find the difference between the limits. 5 over n squared we can write as a product. You don't need to write this because this is also 1 over infinity, and limit 1 over infinity is 0. But in this case, we want to show that we can use the product rule for proving this limit. These are two important limits. X to the n when n approaches infinity. If absolute value of x is less than 1, if you take that value to some power and the power increases, then this term will decrease and approach to 0. So it means that for any x with absolute value of x less than 1, this limit is 0. The second one is another important limit, 1 plus x over n to the n for any x approaches to e to the x. Or in general, if I have a divided by n, b times n plus c for any a, b, c, this is e to the a times b. Like this one, minus 1/2 has absolute value less than 1. Then if we take that 1 to the nth power, the sequence approaches 0, or it converges to 0. Second one, we can write 1 plus minus 2 over n. In this case, a is minus 2, b is 1, c is 0, e to the a times b is e to the minus 2. The sequence is called non-decreasing if satisfy this property, an is less than or equal to an plus 1. Like this sequence, I have the first term 5, the second term is 7, the third term is still 7, and then 8. So we can see that from 7 to 7 it's not increasing. It can stay constant or increase. Increase, stay constant. If this thing happens, it is not strictly increasing, but we call this one non-decreasing. Means that it goes upward, remain constant in some interval, it may go upward. So it's not going down, means that it is non-decreasing. But this sequence 1, 2, 3, so it's strictly increasing, 1/2, 2/3, strictly increasing. This is not increasing, but since it's always constant, can still say that this is non-decreasing sequence. We call a sequence bounded from above if all terms of the sequence are less than m for any n. All terms are, this is an upper bound. And the smallest value for m, that all terms of sequence are less than that, is called the least upper bound. The smallest value or least upper bound means if L is the least upper bound, if I go below a little bit, find another number smallest than L, like L minus epsilon for any small epsilon, still we can find some an which is after that. It means that it is not anymore an upper bound. If this happens, then we say that this L is the least upper bound. L is upper bound, but for any epsilon, L minus epsilon is not an upper bound. So this is least upper bound. And we have the theorem that if a sequence is non-decreasing and it has upper bound, then it will converge to its least upper bound. So least upper bound is going to be the limit of this sequence. Any non-decreasing sequence which is bounded from above converges to its least upper bound. And that least upper bound exactly is the supremum of an. So the same can be defined for bounded from below or greatest lower bound. If I have a sequence which is non-increasing, but we have a lower bound, it means that the terms of sequence are not going to pass this, then there exists greatest lower bound that all terms of sequence are above that, and this sequence converges to its greatest lower bound, and in this case it's exactly the infimum of an. So a non-decreasing sequence converges if and only if it is bounded from above. If a non-decreasing sequence converges, it converges to its least upper bound. So this is an upper bound like M. Least upper bound means, so here if this is an upper bound, so this is also another upper bound, this is also another upper bound, or after M, this is also another upper bound, but among these upper bounds, this is the smallest or least upper bound. It means that if I draw any other line below this, then there will be at least some terms of the sequence after that. It means that this is not the upper bound anymore, or this is the least upper bound. If I want to calculate limit of sequences like this is a kind of composite function. We can see that 1 plus 1 over n to the n, 1 plus 1 over n to the n when approaches to infinity. A is 1, b is 1, c is 0. So this one approaches to e. So this ln is a continuous function. So this one also will approach to ln e. And we know that e, or e to the 1, ln e to the 1 is the 1 itself. So this sequence converges to 1. This sequence we can write 1 plus, instead of that, I can write this one as n plus 1 over n to the minus n. We can find the reciprocal and then write the negative sign here. Reciprocal of reciprocal is the terms itself. And it is 1 plus 1 over n to the minus n. Now here a and b, a is 1, b is minus 1, so this is e to the minus 1. For this one, we can use some substitution, or we can rewrite this one also as 3n plus 1 divided by 3n, 3n minus 1 divided by 3n. To the nth power, to the nth power. If we simplify, we can get the same thing. Now, if we rewrite this, in the numerator, I'm going to have 1 plus 1/3 over n. And here also, we are going to have 1 minus 1 plus 1/3 over n, but this is minus to the n. Now, numerator approaches to e to the 1/3, denominator e to the minus 1/3. So we have e to the 1/3 divided by e to the minus 1/3, or e to the 2 over 3. Sometimes the exercise may give you some epsilon and ask you to find the L that gives you all terms of sequence to be in this interval for a given epsilon for any n after that n. So we are going to have this type of exercise as well. If the general term is not given, we may have a sequence defined in a recursive form or with a recursion formula. It means that terms of sequence are defined by one or more terms before that. For example, in this case, A2 is defined by A1 plus 1. It means that A2 is defined by one term, or AN defined by one term. Before that, AN is defined by AN minus 1 plus 1. And we need one initial value if we use one term to determine. Or if I study the Fibonacci formula or Fibonacci numbers, this is another recursive definition. AN plus 1 is AN plus AN minus 1. It means that to find the n plus 1 term, we need to add the previous two terms. So in this case, we need two initial values. If we have two initial values given, we can give all the terms of the sequence. And we will find the limit of this type of sequences and study whether the sequence is monotone, whether it's bounded or not. And in case that it is monotone and bounded, then it has a limit, then we can find the limit easily.